In this lesson, we are going to be looking at a very specific type of calculation known as percent error and how you deal with significant figures in rounding your calculated answers. So let's talk first about what percent error does for us, right? So if you have a measurement, that measurement can be considered accurate or inaccurate depending on how close the measurement is to what is called the accepted value, right? There's usually like a value for a particular measurement that is agreed upon, and when you are doing an experiment, you have to compare your answer to the accepted value. So let's say you're doing an experiment to determine the density of a sample of aluminum metal. In this experiment, you measure the mass and the volume of a sample of aluminum, and then you calculate the density to be 2.49 grams per cubic centimeter. This value is referred to as the experimental or the measured value. And when we compare that to our reference table S, right, if we go to reference table S and find aluminum, here's aluminum right here. If we read over here, we can find that the density of aluminum is 2.70 grams per cubic centimeters. So we find that the accepted value for the density of aluminum is 2.70 grams per cubic centimeters. That's what we call the accepted value. So the error of an experiment is the difference between the measured and the accepted value. And so the error in this experiment can be calculated here. And again, this is going to be an absolute value, so it doesn't matter which number we subtract from the other. But if we take 2.70 grams per cubic centimeter and subtract 2.49 grams per cubic centimeter and put that in absolute value brackets, right? 2.70 minus 2.49, we are going to get 0.21 grams per cubic centimeter. That's what's considered the error, how far off you were from the accepted value. Okay. So absolute value here is what we are going to use these bars to avoid the confusion of a negative error. We don't want this number to be, this number needs to represent a magnitude, not like which side of the error you are on. And as you know, an absolute value is will make any number positive. So what we're now going to do is we're going to divide the error, right? That's our error that we figured out up here. We're going to divide that by the accepted value and then multiply by 100 to put it into percent form. That's what we're going to call percent error. So percent error is going to be the error of 0.21 grams per cubic centimeter divided by the accepted value, which is the one we got from the reference tables, of 2.70 grams per cubic centimeter. Notice that these units will cancel out. Putting it into percent form, we have to multiply by 100. And when we do this math, 0.21 divided by 2.70, and we get this crazy number. We are going to then multiply by 100, and we are going to get 7 point. Now let's take a look at significant figures. We're dividing 2 sig figs divided by 3 sig figs, so our answer here should have 2 significant figures. So this would have to be 7.8% error. Okay. All right. Now, this percent error equation can be found in your reference tables. When we go to the very back page of your reference tables, you will see formulas and equations. And second one down, or third one down, you'll find percent error. It is the measured value minus the accepted value. It's okay to put, go ahead and pencil that onto your reference tables. That's an absolute value of measured minus accepted. although since its absolute value could be either way, could be accepted minus measured, divided by the accepted value, and then the whole thing multiplied by 100. So let's copy this down, right? Percent error equals the measured minus the accepted in absolute value brackets, divided by accepted, multiplied by 100. A note about interpreting percent error. When the measured value is equal to the accepted value, then the percent error is 0%. And as the accuracy of a measurement increases, as you get closer and closer to the known value, the accepted value, the percent error is going to decrease. It's an inverse relationship. As you get more accurate, your percent error decreases. In this class, a percent error less than 5% is considered good and represents quality lab skills and that the lab methods had few flaws. Or you just got lucky. A note about significant figures. In a percent error problem, the numerator is a subtraction problem. The answer here must be rounded according to the addition-subtraction rules and reflect the least precise measurement. As you recall, in a subtraction problem, the answer should represent the fewest digits after the decimal. But after you round the numerator answer, you're then going to have to divide. And that answer must then be rounded according to the multiplication division rules. The answer now should represent the fewest total number of sig figs. Right? We can see that here in this problem, which is more of a physics problem than a chemistry problem, but we've got the acceleration of gravity in meters per second squared. So here's the measured value minus the accepted value. When we subtract those two, fewest digits after the decimal, they both have 2 digits after the decimal, so the subtracted answer has to have 2 digits after the decimal. But when you're dividing by 9.8, right, you're dividing by 1 sig fig divided by 3 sig figs. So that means your answer can only have one significant figure. Okay, so this is tricky about this type of problem when you're figuring out how to round your answers. Now, note about units. Notice what happens to the units in a percent error problem. When you subtracted 9.73 minus 9.80, that unit right there should have been in meters per second squared. 9.80 is meters per second squared. But in the end, those units cancel out. And the only symbol you should show at the end of your calculation is a percent sign. All right, this lesson has been a up-close and personal review of how you do a percent error problem and how you go about rounding your answers. That's it for this video lesson. We'll see you back in the classroom.